So this is vibrational dynamics and the solution for tutorial 2, which is covering the first part of chapter 2. So in this problem we have a wind turbine, and the question is around a blade which passes the supporting tower is actually forced by the wind, and we're assuming that this force is going to be a sinusoid with a certain amplitude and a certain frequency. We're told that the rotor operates at 6 revolutions per minute in normal wind conditions, and then we have some data around the actual blade of a mass of 8 tons supported by a spring coefficient K and a damping of The first part of this question asks us to evaluate the forcing frequency omega in radians per second under normal operations. Well, we've got actually the forcing frequency. It's given to us as 6 revolutions per minute, but we need to convert that to radians per second for it to work in our solution. So part A is simply to work out what omega is, and we know that this is 6 revolutions per minute, and we apply some conversion factors. So we know that in 1 minute we have 60 seconds, and in 1 revolution we have 2 pi radians. And as long as your units cancel, we're going to end up with radians per second, and if you do the sums, this comes out to be 0.6283 radians per second. And so this is our forcing frequency, omega. Part B says, what is the natural frequency of the blade? So for part B, we simply employ the equation that we've seen before. Omega naught is the square root of K divided by M. We've got K and M, so we're going to stick the numbers in. We've got 39240 for K. M is 8 tons. 8 times 10 to the 3. And if you do those sums, that comes to 2.2147 radians per second. So that's our omega naught. Now part C, it says under a particular wind regime, the fluctuating force on the blade attains a peak value of 2 kilonewtons. So that's our amplitude of the forcing function. And then it says determine the amplitude and its phase relationship to the force, and hence the equation representing the displacement of the blade tip. And so if we go to sections 2.2 to 2.4 of the course notes, and we look up a forced damped problem, which is what this is, we have a force being applied to a system that's got damping, then we know the solution is going to look something like this. X of t is going to be a cosine of omega t minus delta. Okay, so that's for a forced damped system. Omega we know, we've got that here as part of the answer to part A, but we need to work out what A and delta are. Now I know that the equations for A and delta require us to know what gamma is, so I'm going to work it out up here so we can refer to it. And so gamma we know is C upon M, and gamma, so C is 3543.56, and M we know is 8 tons, 8 times 10 to the 3. And if you do those sums, that comes out to be 0.4429. So let's work this out. We know from equation 2.35, that gives us an equation for A, which is F naught divided by M, 1 divided by the square root of omega naught squared minus omega squared, quantity squared, plus omega gamma squared, all square rooted. So let's plug in the values. We know that F naught is 2 kilonewtons, and the mass is 8 tons. Then we've got 1 divided by, and we simply stick in our values that we've been calculating. So that's 2.2147 squared minus 0.6283 squared, quantity squared, plus 0.6283 times by 0.4429 quantity squared, and the whole thing is square rooted. And if you do the sums on your calculator, you get 0.0553 meters. Now to work out what delta is, we're going to use equation 2.36. So that says that delta is the inverse tangent of omega gamma divided by omega naught squared minus omega squared. And if we do those sums, that's the inverse tangent 0.6283 times 0.4429 divided by 2.2147 squared minus 0.6283 squared. If you do that sum, that comes out to be 0.0616 radians. And so to get the equation, we simply plug those values back into our equation of motion, which is x of t, is up here, a, so 0.0553, cosine, omega, which is 0.6283, time, minus 0.0616 radians. And there is our solution, our equation of motion for the system. For part D, it says plot the resulting equation using MATLAB. What is the effect of on amplitude and frequency of oscillation if the rotor is operating at 8 revolutions per minute? Well, if the rotor is operating at 8 revolutions per minute, the value that's going to change is going to be omega, and that will obviously have consequential impact on the amplitude and the phase. And to see what that looks like, take a look at the MATLAB code T2.m.